I guess we can start the afternoon session. The first speaker of the afternoon session is Professor I.Ip from HKUST at Hong Kong. He's going to talk about regular positive representations.
So thank you very much for the invitation. So today I'm going to talk about some recent development of the theory called positive representations, which is a certain kind of representations of quantum groups that I would like to introduce. So there are two sides of the story. One is the algebraic side and one is the analytic side. So the basic algebraic setup is that we have a quantum group, UQG. So I'll just specify G to be semi-simple type. And well, for calculation purpose, usually it's just simple types. And on one side, we have quantum groups, and we want to realize the representation of quantum groups using another algebraic structure called quantum cluster algebra. So when you talk about cluster algebra, it is usually associated to some quiver, some arrow diagrams, and we are looking at the quantum version of this of the cluster algebra associated to Q. So there are these regular functions, and so the goal is to realize the quantum groups embedded into some regular functions of this quantum cluster algebra. So that's the algebraic setup, and the motivation for doing this is the original goal to study the quantum group in a very special circumstances, which is the split real form of quantum groups. So in addition to just usual representation theory, I want to realize the generators of the quantum groups in terms of positive operators acting on some Hilbert space. So in this story, the setup on the cluster algebra side is that we would like to find certain polarization of the cluster variables. So this means that we are realizing the quantum cluster variables using the Heisenberg operators, which are the position and momentum operator. They are self-adjoint or symmetric operators, but you can extend to self-adjoint operator acting on some Hilbert space. And if you have a representation of, so if you have a representation of the variables associated to this quantum cluster algebra, then you can pull back to a representation of the quantum groups, and that will induce a representation where the generators will act by positive self-adjoint or essentially self-adjoint operators. So they are on the, and we will see some examples later. So that's the setup, and the goal is try to classify representations of quantum groups obtained this way. So we want to basically find a map from quantum group to quantum cluster algebra, realize some kind of representation on this side, and pull back to the quantum groups. And it is regular in the sense that these are regular functions on all cluster seeds. So in cluster algebra, you can do mutations, if you know. And so if you do mutations, it will correspond to unitary equivalence on the Hilbert space. and the map from the quantum groups to this side will require that the image are always universally Laurent. So it will be Laurent polynomials in every seed mutation equivalent to the initial one. Yeah, so basically that's the setup. So I'll try to introduce the terminologies and some notations one by one. So first of all, quantum groups. So just to set up notations, so my quantum group usually is indexed by E and F and K. So K is the Cartan generators with the standard Q commutation relations, the Hopf algebra structure, the coproduct. So this is UQ SL2, and Q here is, for now, is a generic parameter, but later we will specify Q to lie on the unit circle. So when we talk about the split real form of quantum groups, so in this case, SL2R, what we want to study is the representation of these generators imposing a star structure such that the generators are self-adjoint. So if you want to realize on some Hilbert space, they should be some self-adjoint operators. And the star should also act by kind of complex conjugation on the parameter. And this, together with the Q commutation relations, will force Q to lie on the unit circle And for simplicity, I guess, we'll restrict to the case where Q is not a root of unity. So B squared is not rational. So this is SL2, and of course, it is easy to generalize these relations to higher ranks, which is well known. So this is the Dreamfield-Jimbo quantized enveloping algebra. So basically, you have more relations indexed by the thinking diagrams, and you also have the cell relations that I did not write it down. And also, depending on whether you are working on simply laced case or non-simply laced case, you have some kind of multipliers on the Q parameters. But otherwise, the relations are more or less the same as SL2. You just have extra relations relating to adjacent nodes in the thinking diagram. And similarly, for the real form, then what I require is the same. We want to study the case when the generators are self-adjoint with the same conditions on Q. Right. So this is just the general definition of quantum groups. And for convenience, we will usually impose one more extra generator, K prime, and study the Dreamfield double instead. So the Dreamfield double, by definition, you just add one more generator called K prime that behaves like K inverse. So instead of K inverse, you write K prime everywhere. And so K prime of E will commute with E and K, but with a minus sign there. So it just looks like K inverse. And so basically, you can recover the original quantum group by portioning out with this ideal. Right, so this will be the main object we are going to study. And so, of course, if you get a representation of the Dreamfield double satisfying the condition that KK prime equals 1, then it will reduce back to a representation of the quantum group. And finally, we need some kind of rescaling. So it's just for convenient purpose. So we are rescaling the main generators with some constant, and this constant is actually just some positive real numbers. So these are just real numbers, and when B is less than 1, this is positive. All right, so a first example, or the very motivation to study this quantum group, is the work by Fadiev and Teschner back in 1999. So they have this representation of UQSL2R, motivated from their study of quantum Liouville field theory in integrable system. So they found such a representation called P lambda. So lambda is a positive number, which is the parameter. And they realized the generators of the quantum SL2 in terms of the position, U, and the momentum operator, which is some kind of differentiation operator, raised to the exponential. So by construction, these are originally symmetric positive operators, and they have, on certain nice dense domain, they have a unique extension to become self-adjoint operators. So they are operators acting on L2R, unbounded, but have like a unique extension to self-adjoint case. So this representation is also irreducible. So in this story, this irreducible will mean that these operators will strongly commute, and any bounded operators strongly commute with these representations will be the scalars. So yeah, because these are self-adjoint, so you have spectral projections, and you require anything commuting with those projections are scalars. So these representations are irreducible, found by Teschner, and you can also study the center of this representation. So these are the Casimir operator. So just like usual SL2 representation, you have the Casimir, and they act as scalar because it commutes with all the generators. We have the same situation in the real case. So you can find operators that commute strongly with all the representations, and they will act by scalars like this. So you can just compute C, and you get a positive scalar bigger than 2. Yeah, so one goal is, yes, question? Yes, yes, so this B is the Q, where's my Q? This B. It's the same B, yes. Right, so we'll be studying the Casimir a lot later. So one aspect of representation theory is that the action of the Casimir, the central characters, will kind of tells you which irreducible representation you have. And later we'll see how these are related. Right, so this is SL2. And so back in my PhD years, together with Igor Frankel, we try to generalize this special kind of representations to higher rank. So we call this a positive representations, which are representations of those quantum group generators by positive operators acting on some Hilbert space. And they looks like some kind of quantization of principal series representation. So they are constructed by looking at the regular representation of G on the complete varieties, and then try to quantize that infinitesimal actions. And we expect that this representation should directly generalize Teschner's representation to higher rank. So the main properties of this family of representation, first is that they are irreducible one, parameterized by not just one number now, but by n numbers. So this is kind of mimicking the dominant weight situation. So it is parameterized by not the discrete weight, but a real span of the dominant weight. And as mentioned, the generators are represented by positive, essentially self-adjoint operators on some Hilbert space. And the functional dimension of this Hilbert space is related to the length of the longest word of the while group. And on the computational side, it turns out that you can actually write down these generators explicitly. And when you write it down, they will be expressed in terms of the exponential to the position and exponential of the momentum. So these are the wild algebra generators. And these are also the main candidate that tells us polarization of cluster variables later. And finally, we also have something called transcendental relations, which is something new compared with the compact case. So that if you replace the B parameter by B inverse in this Q thing, then what you get will be another related copies of the quantum group, but it will depend on the type of the quantum group. So if it is non-simplest type, then you can actually see some Langlands duality there, where the long root generators will swap with the short root generators in the representation. But today we are not going to focus too much on this aspect of the story. So yeah, 10, 12 years ago, when I construct this representation, it's kind of ad hoc brute force calculations using the regular representations. And then later we found that these expressions can be easily understood in terms of quantum cluster algebras. So this is the next object that I would like to recall. Yeah, so it's all start with Fogg and Koncharov's work, of course. So the quantum torus algebra are like the quantization of each seed of the cluster X variety. So the basic setup is the following. So you have a seed which consists of 4 data, the nodes of the quiver, and some part of the nodes are frozen. So there are some special nodes you don't do anything to them. Then you have the exchange matrix. So this will be skew symmetrizable matrix. And in the standard sense, when Q is just quiver, this B will be the adjacency matrix. So how many arrows from one node to the another. And we allowed half integer values in the special case when you talk about arrows between the frozen nodes. And finally, in the non-simplest case, we will also allow some kind of multipliers. But if we are only interested in ADE type, then you can just take all the D's to be 1. In any case, we will construct from the exchange matrix a skew symmetric version of it, and then define the quantum torus algebra associated to this quiver. So the generators will be indexed by the nodes of the quiver. And whenever you have an arrow between 2 nodes, then you will have a Q commutation relations between them. So basically, you have a bunch of X with a bunch of Q commutation relations to define that algebra. So this is just for one seed, so we haven't talked about the mutations yet. The generators are the variables, cluster variables. I mean, for now, it is polynomial here. Not Laurent yet, I think. Yeah. Do I want to? Well, we'll see later because yeah, for now maybe invertible. Yeah. Well, quantum torus maybe. Yeah, maybe I should put invertible. Yeah. Oh yeah. If I write this way, then it is invertible. Yes. Yeah. So another way to present the same information is to impose a skew symmetric form, realizing that skew symmetric matrix. Then the generators can be realized instead of the index. You can use the elements from the C lattice. Yeah. So probably it should be invertible. So I can allow minus here, which becomes minus inverse. Yeah. So this will be the notation relating the two. So xi will correspond to x of the basis ei. Right, so as an example, how to present this pictorially. So given a seed with the adjacency, with the exchange matrix, I can use a adjacency matrix to represent the quiver. So in the diagram, if I have an arrow from I to j, then it will correspond to a Q commutation relations between xi and xj. And the Q factors will depend on the multiplier of the seed. And as mentioned, when we have frozen variables, then we allow half the weight only. So you just divide the weight by 1/2. So this will be my convention. And also there will be situations when I have different weights. So pictorially, I will use like thin arrow and thick arrow to distinguish them. But the thickness are not part of the data because we already know the multipliers, then we should already know the Q commutations between them. But so it's just a mnemonic device for me to memorize the Q commutation relations. So for example, 2 and 3 will commute with bigger power of 4 because of this weight. Not because of the thickness, but I will indicate with that. Yeah. Right, so with the quantum torus algebra and also with this the setup of the real case, the polarization of such variables will be an assignment of these variables to exponential of some self-adjoint operators. So this exponential, xk, will be combinations of the momentum and position, just like the SL2 representations earlier, probably with some scalars together, in such a way that the commutation relations between the x and k will recover the exchange matrix of that quiver. So if you raise this x back to the exponential, then the capital X variables will satisfy that Q commutation relations. So this will be operators acting on Hilbert space. The dimension of this Hilbert space will depend on the number of number of vertices in the quiver, and there are several choices of that can be. There are several choices of that depending on whether you want the polarization to be irreducible or not. So this M is not important for now, but there exists such a polarization. And also for the modular double, the B with B inverse 1 will be related by taking some kind of powers of 1/b squared. And this will make sense as positive operators if these are essentially self-adjoint. You can use functional calculus to extend the powers. Yeah, so for example, if we have just a very simple commutation relation, x1, x2 equals q squared, x2, x1, then we can just assign the two polarization to x1 and x2 as follows, and this will give us positive operators on the standard L2R. And again, just to remind that these are unbounded operators. So when we talk about commutation relations, of this type, what we have in mind, there are two ways usually. One is to restrict these operators to some dense subspace such that the product makes sense. Or one can use functional calculus and raise these two to complex powers to make them unitary and consider this equation as relations among bounded operators. But yeah, for us, let's just consider this algebraically and treat these two as satisfying this relation on some nice dense subspace. So some terminologies here. We have an algebra generated by the X, so we can calculate the center of this algebra. And the center turns out to be just monomials of these X variables. And you can find the number of these variables given by the size of the quiver minus the rank of the exchange matrix. And we'll just say that the polarization is irreducible if all the central monomials act by a scalar. Then it is known that if you have two irreducible polarization acting with the same scalar of where the central monomials act by the same scalar, then they are unitary equivalent. You can actually find an explicit change of variables on the X and on the U's and P's to match the two polarization. Right, so the previous setup is just for one single seed. You have one quiver, one algebra associated with this quiver, and then the polarization. And for cluster algebra story, the most important feature is that there are something called mutations. So you can change from one seed to another seed using some bidirectional isomorphisms. And in the quantum case, you can also do that. And these are some horrible formula if you haven't seen it. But when you have the classical limit, when Q goes to 1, it becomes the standard cluster algebra mutation formulas. So basically, given a cluster variables, you can associate to it a neo-rational expression of cluster variables in another seed, and then everything somehow becomes compatible. And these mutations can also be decomposed into two parts for calculation. One part is given by some monomial transformation. So either you take inverse or you have some products of the cluster variables, and you put in this Q to make this whole thing self-adjoint again. And so this is the monomial transform followed by something called a quantum dilogarithm transform. So you conjugate by some special function called quantum dilogarithms in order to produce this kind of product above. Yeah, so now if you have a polarization, the representation on one seed, and you have a cluster mutations, then it turns out that you can easily associate a new polarization to the new seed by just changing the polarization of each variables using just the monomial transform. And in that case, cluster mutations will correspond to unitary transformation between the two Hilbert space. So you have one Hilbert space corresponds to one seed, another Hilbert space corresponds to another seed. You have one polarization, you have another polarization, then these two will be related by a unitary equivalence. Which means if you have a representation on one Hilbert space with one seed, you can easily bring it to a representation on another Hilbert space with another seed under the same unitary transform. Yeah, so with cluster, with quantum cluster algebra, you can talk about the upper cluster algebra. So by definition, these are the elements of the cluster algebra such that they are, first of all, Laurent polynomial. So they are Laurent expressions in the X. And they should still be Laurent polynomials under any quantum cluster mutations. So if you have a Laurent expressions and you apply these horrible mutation formulas, you should still get back some Laurent polynomial without like bad denominators. Right, so these are the quantum upper cluster algebra. And so because of that property, we will call elements of that universally Laurent polynomials. And then every polarization of the cluster variables will induce a polarization of this subalgebra. Right, so this is the general setup. And so now what is the correct quiver that relates the whole story between quantum groups and quantum cluster variety will be the one associated by Fock and Goncharov. So in general, if you have a Riemann surface with boundaries and mark points, on boundary and punctures, what we have will be a moduli space of frame local G system. So these are the moduli space of flat principal G bundle with flat connections with some additional structure. And so what they did is that they associate some Poisson cluster X variety structure on this. And with the Poisson structure, you can quantize them to become a quantum cluster algebra. But what we are interested in is just the information associated to this. So we want to know what quiver gives you the cluster variety. In the SLN case, or GLN+1 type A, basic type A case, the quiver is associated with something called an N triangulation. So it is kind of S3 symmetric quiver. So in general, this is done for arbitrary type. So basically, if you have a Riemann surface, you have a triangulation of this Riemann surface. Then you associate some basic quiver to each triangle, and you try to glue them all together on the surface. So this is done in full generality in one of my early paper and Ian Ness, and later Goncharov gives a really complete geometric pictures, complete description from the geometric point of view, I would say. Yeah, that how to construct such a basic quiver for all types. And so basically the main ingredient will be the longest word W0 of the while group. From this longest word, you can construct this quiver in a canonical way. And then from this quiver, you can associate such an algebra. So this will be the quantum torus algebra associated to this quiver, and then you talk about mutations and all this stuff. Right. So the assignment of this quiver to the surface is also compatible with the choice of triangulation, because for each surface, you might have different choice of triangulations related by flip of the diagonals. And it turns out that if you flip the diagonal, then it just corresponds to mutating several nodes of this quiver. So in type A case, type AN case, you will require n+2 choose 3 mutations. I think you do the mirror one, 1, 2, 3, and then you do the middle one, 4, 5, 6, 7, and then you do the horizontal ones, and then you will get this mutation, this quiver.
The arrows on the right.
Sorry, say again?
The arrows on the right.
Arrows on the right.
They have varying.
It's a LaTeX problem, probably. It should be the same, all the same. Yes. I mean, it's type A, so simply this. Yeah, so in SL4, you have 10 mutations. And this sequence of mutations are done for arbitrary types. So for type E8, you have crazy quivers. You can find the mutations bringing one to the other picture. Right, so the quantum group representations is constructed using the following strategy. So you start with 2 quivers, one on each triangle, and the other is like opposite arrows. But they are actually the same, but just rotated 180 degrees. But in any case, the construction, remember, is that you have the longest element. So in this case, actually, this arrow is correspond 1, 2, 1, 3, 2, 1. So it's the while group element. The opposite indicates that you use the different ordering on the while group. Anyway, so you have 2 such triangles. Then you can glue them together, which Fock and Goncharov call them amalgamation. So if you glue them together, the frozens will become unfrozen, and the dotted arrows will add or subtract depending on the direction. And you end up with such a quiver at the end. So one important discovery by Schroeder-Shapiro is that if you look at this quiver, then you have a very nice embedding of the Dreamfield-Stubble quantum group that we discussed earlier into the quantum torus algebra associated to this quiver. And in particular, if you quotient by this kk prime equals 1 ideal, then you get the embedding of quantum groups itself. So it turns out this is really easy to describe. So to describe the embedding, we just need to know where the generators go. So the F generators, the lower Borel generators, will be embedded into this quiver by some telescopic sums. So this is the notations I used earlier. So it's like the product of x1, x2, x3 with some q powers in front to normalize. So these are like a telescopic sum. The F1 generators are the polynomial of x1 up to x6 along this path, and F2, F3 similar. K prime will be the Dreamfield's Cartan variables, and it is just the product of all the variables along the blue line. And due to symmetry, you can actually tell the E generators also. So the E generators will be going on the other direction. So one checks that algebraically, this gives a realization of the quantum group Chevrolet generators in terms of these cluster variables. So you can check, for example, E1, E2, E1, does the cell relation is satisfied as an element in the quantum torus algebra. Right, so this is for SL2, SLN case, and it turns out that it works for all other types. So the main theorem is that we choose the surface with 2 mark points and 1 puncture, so that the triangulation is just 2 triangles here, but then you glue the 2 sides together. Then there will be an embedding of the Dreamfield's double to this quantum torus algebra, where each triangle is associated that basic quiver. And in particular, if I have this embedding, and if I can choose a polarized, irreducible polarization on the right-hand side, then I get a representation of the Dreamfield's double. And it turns out it is exactly the positive representations that I constructed like many years ago.
Not much choice.
Sorry.
You're going to embed the Dreamfield double and
Yes. So I think there's a result of construction that says these are actually isomorphic to the while invariant part of that quantum cluster. So you have a while group action on the right-hand side, then there's an isomorphism between them. Yeah, but also this will depend on the choice of the seed, because you can do mutations on one side and then you get another expressions of the quantum group. Yeah, so the main result is that you will have the embedding of the quantum group to the quantum cluster algebra, but not just on one seed, but it actually works on every seed. So on every seed, you actually get a universal Laurent polynomial. So if you do mutations, you won't get bad denominators in the expressions. And one half of the path, in my case, the lower Borel paths are simple, and they actually recover Fagin's homomorphisms of the lower Borel quantum part to some quantum torus algebra. Yeah. So this is described for all types. And so what this gives me the motivation to ask whether these are all the possible representations. Yes?
Is there also a quotient where you get the U2?
Yes, sure. Here. Oh, no, this one probably you don't need quotient because there's no kk prime. K prime is the 2 different Borel parts. Right? So there's no quotient here. Right, so yeah, as John Duncan asked whether these are all the representations, and yeah, so that's the main question. We want to study basically all such representation so that you have an embedding of you have a map of the quantum group in terms of some universally Laurent expressions. So in other words, we will say a representation to be regular if there exists a map from the quantum Dreamfield's double to the quantum upper cluster algebra such that all the generators are universally Laurent. But it turns out that in all the known cases so far, they are not just universally Laurent, but they are actually universally polynomials. So you never have negative powers of those x. Yeah, so this is recently proved with my MPhil student using actually sign coherence of C vectors in cluster algebras. But we are not going to delve into detail there.
Why is it specified? It's for some cases.
So in every case, we have these properties. We are not sure whether this is a characterizing properties of such a class. Yes. Yes. Yeah, so in particular, if you quotient by this kk prime equals 1, you will get the quantum group representations. Yeah, so the main question is try to classify such representations, irreducible ones. And the previous question, whether the Casimers of this representation will tell us things about those special class. Right, so it turns out that there are other class of representations that realize your quantum group generators as positive operators, but not of the previous class. So one big family is called the positive representations. So just to recall a little bit, the standard one, the one we just mentioned, is constructed by quantizing the principal series representations. So it is really quantizing the induced representation of G on some Borel subgroup. So instead of taking the Borel subgroup, we can actually replace this by a bigger subgroup, the parabolic subgroup. So in a parabolic subgroup, the subgroup will be indexed by some J. J is a subset of the thinking index. The usual one, the Borel one, will correspond to J empty set. Yeah, so as a general picture, so if you have a subset of the thinking index, then you can split the longest word into two parts, one with the smaller index vowel group and then the rest. So for example, if you have 1 to 1, 3 to 1 of SL4, then WJ may be just 1 to 1 here. So this will be the longest word for the SL3 part together with the rest of the vowel group. And if you realize this way, then we found that the quiver that we constructed earlier also has a decomposition using such a parabolic truncation. So I think that's an example. Yes. So this is the SL4 quiver that we just saw earlier. And if you look closely, you can see that this whole part, this hexagon part, is actually a quiver for the SL3. Yeah, SL3, right? Yeah, so the whole quiver can be decomposed into the remaining part, and then the SL3 part, and then the remaining part. And so the construction of the parabolic representation is that you can safely truncate away that SL3 part. So you squeeze the SL3 part together, and you will get such a quiver. Right, so can you compare this? So it's like 16 to 9, 14 glued with 16, 6, 11, 14. You squeeze it and you get this quiver. So this quiver is just the amalgamation of the remaining part of the original quiver. And it turns out that this process gives you a well-defined, not embedding, but the homomorphisms of the quantum Dreamfield double into the quantum torus algebra of this quiver. So this is what we call the parabolic representation. And you can actually just write down, as before, some telescopic sums along these colored arrows. Yeah, so that's the main theorem, is that we have a homomorphisms from the Dreamfield double to this truncated version of the quantum torus algebra. And again, they are not just universally Laurent, so it is in the regular part, but they are actually universally polynomials. There are no negative powers of the cluster variables. And again, because this is just a quantum torus algebra, you can talk about the polarization. You can find the irreducible one, and it will pull back to a representation of the quantum group using positive self-adjoint operators on some smaller Hilbert space. Yeah, so as a bigger example, this is the E6 quiver. So this is actually two parts, the Q opposite and Q quiver glued together. So this is the E6 quiver, and there are a chain of parabolic subgroups inside this E6. So for example, if I take the D5 inside E6, which is the colored portion of this quiver, you truncate it, you squeeze them together, you will get such a quiver, and this gives a new representation of the E6 quantum groups that is not known before. Yeah, so in the E-type, the Fagan's homomorphism, the lower Borel part is actually very nice. All the F's are just horizontal lines, so they're just the telescopic sum along the horizontal lines. But the E generators are quite chaotic, so it just go up and down along this quiver, but still in a telescopic sums manner. And the algorithm also works for non-simplest type. So for example, this is type B5. You have some short roots and some long roots. The thick one is the long roots. These are the short roots. And you have the A4 part inside B5. And again, you can just truncate it to get some, I don't know, Christmas tree thing. So then is that all we get? It turns out there are yet another special class of representations that we found later. So let's go back to the SL2 situation. So in SL2, the situation is very simple. This is the Teschner's representation. If you still remember Teschner's one, you just have one variable, L2R, and it can be written as the sum of two operators for E and F, and some exponential for the K. Yeah, so this is the SL2 embedding. And the previous Casimir, the e to the lambda plus e to the minus lambda thing, is just given by these two terms. And you can check that 1, 3 is a center of this quiver, for example. Yeah, so if you further impose that the kk prime equals 1, then get a polarization, then you recover Teschner's p lambda from this picture. So this is the beginning of the whole story. And now let's try to do a mutation to this quiver. So if I do a mutation at 2, for example, then I get a new quiver. And with the quantum mutation, I will have the new expression for my embedding, because it also changed with the quantum mutations. And you can see that it is still polynomial without minus powers. And now with this very special form, we see that the 2-node and the 4-node actually are symmetric. They behave the same in the same setting. And also it appears in the Casimir that the 2 and 4 are kind of symmetric expressions. So what's the idea is that we can actually rewrite the embedding here, this part, using the Casimir, like this. But Casimir just acts by scalar. So why restrict the Casimir to act by this lambda plus minus lambda thing? I can just replace C by any complex numbers, and this still gives me a valid representation. In particular, if I replace C by 0, then I get an expression of this type, and it turns out that when C equals 0, the corresponding pictures is equivalent to identifying the 2 and 4 nodes previously into a single node, but with bigger multiplier, with bigger weight. And so now the arrows now is thick. It becomes thick arrow with a new weight. And it turns out that this is a valid quantum torus algebra with custom mutations, and the embedding of these quantum groups to embedding of this quantum group to this quiver also respect the quantum mutations previously. But now the C is set to 0. So we obtain something called the degenerate representation, P0, where this 0 signifies the fact that we are kind of forcing C to 0. And it turns out that this construction works for type AN. And so to remind some terminologies here, what we want to set is the Casimir to 0, but what are Casimirs in higher rank? So there's this construction where to create the center of the quantum groups, you take the R matrix the universal R matrix of the quantum group, and you restrict to some fundamental representations, and then take the quantum trace of that thing, and you can prove that the resulting expression you get will be some expressions that commute with your quantum group. So this is what we call the generalized Casimir. And there are slight modifications of these special elements here to make sure that the eigenvalues of this C will be positive. Anyway, so there's this constructions from universal R matrix to the center of the quantum groups. In SL2, this is the one we have just seen. For SL3, you will get these kind of expressions where the E's will be paired with F. There are some non-simple version of the roots given by the Q commutators. Right, so these are the the Casimirs. So they commute with E and F and K's. So it turns out you can actually compute the eigenvalues of this generalized Casimir on the standard representation using some kind of wild character formulas. So the special case in type AN is the situation is better because we kind of know what are the fundamental representations. They are the symmetric powers. So in particular, the generalized Casimir value will be given by some elementary symmetric polynomials. And this turns out to be a very important observation. In SL3, you can see that these are the expressions, and yeah, there's this symmetry between lambda 1 and lambda 2 permuting whatever. Yeah, so they can be expressed in terms of elementary symmetric polynomials. So how can this help with the type AN situation? Is the trick employed by Schroeder and Shapiro on their study of the UQSLN cluster structure. So let's again start with a Quiffer for this time it is SL5 type A4. So this is the Quiffer we have. So here I also added in the green arrows. So the green arrows actually generate the center of this. I mean, it's part of the center of the quantum cluster algebra. So the product of these nodes lies in the center. So they act by scalar because we require the polarization to be irreducible. And also for quantum groups, we also require the polarization of kk prime equals 1. Right. So what we want to do will be to do a flip of triangulations. But remember, this is our surface. This is my triangulation. So if I try to flip this diagonal, then it will become this kind of picture. So I flip the diagonal of the triangles. I get this. So I have some self-folded part of the Quiffer. So if I do this flipping using the trick mentioned in the previous slide, I will recover such a diagram. Right. So the blue are still the F embedding. The colored ones are the E embedding. So the E embeddings are kind of nice, except the green one, which travels kind of around the whole thing and go back. And now it turns out that there's a trick to further simplify this Quiffer. And what you get is they call the candy Quiffer. So you can actually mutate in such a way that you get a symmetric setup of 4 nodes. Each corresponds to the previous central characters. Yeah, and then it turns out that the F embedding is still the same. The E embedding is also nice, except for one generator, the green one, which kind of travels around all the symmetric nodes and then go back. And the way they depends on these symmetric nodes are exactly the elementary symmetric functions corresponding to the Casimir. So the previous tricks will work if we identify these 5 nodes as a single one with a new multiplier. Is exactly the same as trying to set all the Casimirs to 0 in the previous one. So yeah, so the previous picture now becomes a cluster algebra, quantum cluster algebra with a non-skew symmetrizable Quiffer. So you have an additional weight 5 vertex here. And by construction, if you look at the embedding of the quantum groups under this quiver, all the generalized customer will act by 0. So this is what we call the positive representations with 0 customer. So these are the main results, again, joined with my other student, that you also have universally polynomials of the image of the quantum group generators. And the representations is irreducible in the previous sense, acting as positive operators, but this time all the customer act by 0. Yeah, so the previous one is the embedding for customer equals 0, but remember we also have this very special candidate called the modular double, that when you replace B by B inverse, you flip the long and short thing. So previously in the customer equals 0, we do our construction such that some nodes become higher weight, which means if I do now the modular double trick, I should get a symmetric pair of this representation where the weight 5 thing becomes weight 1/5, for example. So it turns out that that will give me another representation related to the modular double. So if I do the same construction before, but now I apply the modular double trick, then it becomes flipped, and I have this new representation. So this term originally is the customer is C equals 0 for B. Now it becomes Q half plus Q minus half for 1 over B. And this is again a valid map from the Dreamfield double to the cluster algebra associated to this new quiver. Yeah, and then again, you can apply any polarization and you get a new representations. Yeah, so you can combine all these constructions part-wise for your quantum group. So if you can find some type A part in your quantum group, then you can apply this parabolic or degenerate or 0 customer to this specific part and create a new representations of that. So it's better to show pictures, I guess, here. Yeah, so this was what we just mentioned. Yeah, so let's look at this picture. So this is the type B5 with the thick long root and the short root here. And for type B5, we have this A4 inside. And previously, we shrunk this A4 to get the parabolic. But now I can also do the symmetric trick and then embed the customer equals 0 situation to get to such quiver. So this is a very surprising, I think quite surprising structure of the quantum version, where you have a non-simply laced quantum group embedded into, not embedded, but a map into a quantum cluster algebra with 3 different weights. You have the B equals 5 weights, you have the 1 weight, and you also have the 1/2 weight corresponds to the short weight. Yeah, so you have a realization of the quantum group into some non-skew symmetric cluster algebra with 3 different weights. Yeah. Yeah, so to end, this is what we now know so far, is that all the irreducible regular positive representations are of one of these types. So either it's the standard one or the parabolic one, where you truncate part of the subgroups. And also the degenerate one, where you truncate part of the type A subgroups into 0 customer, or apply the modular double counterpart to those type A's, and combinations of those. Yeah, so the question is whether these are all possible ways to find such regular representations, regular positive representations. Yeah, so this is a list of examples of the representations of type A2 that we know so far, so SL3. So we have 2 customers, right? We have 2 customers, and as I mentioned, that one of the goals is to try to understand how the customers tells us what representations we have. So the table is like this. So this is the original customer action of the standard representation. So the standard representation is parameterized by the real span of the dominant weight, so it's 2D. So you have lambda 1 and lambda 2. And then for the parabolic, you can either choose the SL2 of the first copy or SL2 of the second copy, and you get two other families of Casimir. You can take the degenerate representation, so you set the Casimir to 0, or you can just take the degenerate of one copy of the SL2, and then you get this and the other. And finally, you have the modular double degeneration. So this will correspond to that, but with B replaced by B inverse. So you get some quantum free, I guess, quantum free numbers. Yeah, so you can try to plot this into the same picture. And it turns out that for generic Qs, so when Q is not root of unity, they are indeed a disjoint family of Casimir values. So different Casimir values will correspond to different class of representations. However, it is unfortunate that when Q is root of unity, these curves can actually intersect. So if these curves intersect, that means you have different representations, but with the same Casimir values. And they are different representations because the dimension of the Hilbert space are different. Some is L2, R2, some is L2, R, for example. But they have the same value of Casimir. Yeah, so understanding what happens in the root of unity case is definitely one of the questions I need to answer. Yeah, so mention some further direction is that recently with joint work with Gus Schroeder and Sasha Shapiro, we try to interpret the regular positive representations using the so-called quantum Hamiltonian reduction. Especially on the parabolic case. So for the parabolic case, it seems that we can find some kind of moment map such that the smaller Hilbert space is the invariant subspace of the bigger one. And to recover the parabolic one from the standard one, you restrict your action to some kind of delta distributions. So this is a work in progress. And in the standard representations, there is this action of Lustig's break group where you can apply this TI to transform your generators, say from E to F. And it turns out in some case, we checked that this also works for the parabolic case. So we want to ask whether these break group actions are still there for general parabolic subgroups, which will tell us something about the DT invariance. Yeah, and then this is the one that we just mentioned, some uniqueness properties for the Casimir values. We know that the Casimir will uniquely determine the classes for SL3, but in general, this is still open, I think. And of course, there's this important question about the braided tensor category structure, which is the original motivation to study this class of representation. Because for SL2, we know that from Teschner's work, if you take the tensor product of two representations, they actually decompose just like the compact case into the same family of positive representations, but this time it is not a direct sum, but a direct integral. So this decomposition is parameterized by a continuous parameter. And this decomposition is done for SLN, I guess, but not other types yet. And it turns out that these are not the only decompositions we know. We also know, for example, the SL2 case when the Casimir at x0, they still decompose into the same class of the original representation, but with a different Panchero measure. So the P0 that we degenerate somehow looks like the complementary series in this story. Yeah, but in general, what happens is still open. And of course, finally, whether there is a generalization to Cosmodee quantum groups or even just quantum affine Lie algebras. So to explain a bit what this means, so let's look at the parabolic representations previously. So this is the one that we squeezed the whole thing except the outer part. And you can see that I can easily loop this 14 back to 0 and create like a ring thing. And if I do that, then this naturally becomes a representation of the affine SL4. And it turns out that in this special case, this is the evaluation module with respect to the minimal parabolic of SL4. And you can do this trick for other representations also. So if you do the evaluation for the standard representation, you get this quiver that kind of lies on the cylinder, embedded into a cylinder. Yeah, so it would be a interesting question to understand what happens when, or whether you can find new realization of the affine quantum algebra also. Yeah, so this is also one of them. If I choose some funny parabolic, I get some kind of chemistry thing. Yeah, yeah. So I think this is one question that I would like to answer to. All right, so I think I will stop here. Thank you very much.